In the previous session, which was filmed several days ago, I'm still finding that one of the there's several, but one of the major bottlenecks is the upload time to YouTube. On a good night or day, it can take me 2.5 hours per 10-12 minute clip. When it's busy, 3 to 4 hours for the same amount of filming. So if I film for several days in a row, I can get such a backlog that it takes me several days to clear it away to upload it all. So that's what I've been doing recently. Now, the previous session, we derived a formula, an expression, for the energy shift, like the perturbation, if you like, the small change in the energy eigenvalues for the spin coupling combined with the relativistic kinetic energy. Now, we didn't go into details about that second phenomenon because it comes out of Dirac's theory, which is relativistic quantum mechanics, and we don't do that at undergrad level. That's M1 and M2, first and second year master's level. But yeah, we used the formula from it, combined those two effects, got a formula that shows you how much the energy, the eigenvalues of the energy operator, in other words the Hamiltonian. So by adding these effects, by adding the spin coupling effect to the Hamiltonian, the spin coupling term, interaction energy if you like, so you get a small change in the Hamiltonian, and corresponding with that you'll get a small change in the energy eigenvalues. So we found a formula for that small change, that delta E if you like. Right? Now here, and I think I said at the end of that last session, the very next thing I'd do would put up some diagrams to give you a feel for how these energies shift a little. Now these are the energy units. I've got like units of energy in these units. Like this is 1 unit of the mass of the electron times c squared, speed of light squared, alpha to the 4th. That alpha is what? The fine structure constant, which is roughly equal to about 1 over 137, the big mystery of modern physics. You know, why does it take that value? Divided by 256, convenient unit. Now, this is taking the case when n is 4, so your atomic quantum number n, for the energy levels. So, and for various values of L for the orbital angular momentum. So 0, 1, 2, 3. So four cases. Okay. Now, when there's no spin-orbit coupling, imagine, and no relativistic kinetic energy effect, then the energy eigenvalue would be here. Right? Okay, now switch on those two things magically, and you'll get this energy correction. The energy will go down a bit, this much. Now, as your angular momentum increases, we'll do the 4 cases one by one. So for L equals 0, then your J, in this case, we're talking spin orbit coupling, right? So J will be L plus S. Well, if L is 0, the first case, then you've only got the S left. So it's spin half. So your J would just be a half. And if you look at that formula that we got for the energy correction, the perturbation and the energy eigenvalue, in the denominator, so underneath, is a J term or an L term. So the smaller the L term is, let me just check it. Let's have a look in the text to see the actual formula for it. A whole bunch of constants divided by n cubed times 1 over j plus a half minus other stuff. So the smaller j is, because it's in the denominator, it's underneath, the larger the energy shift. Okay, the larger the energy shift. So as j gets larger, the energy change, the perturbation in the eigenvalue of the energy, will get smaller. I hope you follow that logic. All right. So these energy corrections, they get smaller progressively as L goes up, and hence J goes up. Okay. Now, in the first case, when L is 0, there's only one value of J, and that's a half. So it doesn't split; it just changes. It just goes down, but there's only just one level. Now for the other values of L, L is 1, 2, 3, when L is 1, you can have plus or minus S, plus or minus a half, spin up, spin down, parallel, anti-parallel, inverted commas, to the angular momentum vector, if you like. So L plus a half and L minus a half, so this energy, and the energy splits in that case. There's a split, there's two values. Here there's only one, because L is 0. So your energy that would have been here is now here and here. There's a split because you have two values of J. J is a half and J is 3 over 2. And when L is 2, L plus or minus a half. So you get 2.5 and 1.5. So 5 over 2 and 3 over 2. So 5. The dust from the air conditioning. It's had a birthday yesterday, so it's now 25th of August. So the weather's actually starting to cool, very nice. So I wouldn't be surprised in a few days, or maximum a week or two, be using the air conditioner for the last time. So the background noise should be a lot quieter. All right. And for L is 2, so it'll be 2 plus or minus a half, so 5 over 2, 3 over 2, and each time you're getting the split in the energies, so it was at this level, now becomes here, and here, so an energy split, there's two allowed energies for those quantum numbers, right? And when L is 3, so J can be 3.5 or 2.5, so 7 over 2 or 5 over 2, 7 over 2, 5 over 2. Right? So, and that's observed with fine instrumentation. This is for hydrogen. The energy splitting, combined spin orbit plus relativistic kinetic energy for sometimes I wonder if I'm getting premature. What's maybe what's it called? When you get really senile Alzheimer. What am I getting? Premature Alzheimer's disease. Right. So this diagram is indicating the energy splitting for hydrogen. The hydrogen spectrum. When you heat up hydrogen, and energy in form of light rays, photons, is given off. You put the photons through prisms and so forth, and you then photograph the light coming through the prism, and you see these various spectral lines, and the spectrum, the whole range of the various frequencies, wavelengths, if you like, of the photons for a given element, a given type of atom. That's called its spectrum. Okay, so you get this splitting of the allowed energies due to the spin orbit coupling effect and the relativistic kinetic energy effect. This will remain mysterious to you for a year or two until we get into relativistic quantum mechanics, Dirac equations, stuff like that. Right? Now, it's only more mentioned here, there's no mathematical modelling given, but you can do something similar with sodium. And why is that? Well, because in some ways it behaves like hydrogen, because it has one valence electron. I'm not sure if you're familiar with the term valence. It's valence electrons are the outer layer, outer shell electrons that take part in chemical bonding with other atoms. Now, in the case, I was just checking actually, because it's been years. I had a look at the atomic number of sodium here, and it's 11, and that means 11 protons, by definition, atomic number. And for neutral sodium, that means 11 electrons orbiting the nucleus, 11 protons. And if you know a bit about the Pauli exclusion principle, and you can solve, we haven't actually done it, but you can build up